Morning, everyone. All right, so we are picking up where we left off in adiabatic processes. We're going to start off with an example, but first I want to give some reminders on some good strategies whenever you encounter these problems. Like most things in thermo, if you know what you're doing, most of the problems are dumb easy. But if you get flustered and forget maybe to write out the first law, or you forget that the ideal gas law is a thing, it's easy to get stuck in a loop. So here's some reminders for ways that you can make sure that you slice through the problems. So it's usually a good idea whenever you have a process that is told to you to be adiabatic or isothermal or isochoric to write out the first law, especially if you're asked about heat, right? Heat is only found in the first law. It's the only equation that contains heat. So just as a reminder, the first law is the change in thermal energy of an object is, well, I'll write it in our standard order, work in plus Q in. And yeah, I'll just write an arrow here, especially if you're asked about heat input or something. Or maybe you're told the heat input. You're probably going to need the first law. So it should be a knee-jerk reaction. Anytime you see this much heat is put in, bang. Told adiabatic process, bang. Instantly write that out. Okay. And there are certain keywords that tell you maybe some of these terms will be 0. Okay, just as a reminder, work in is always, all right, I shouldn't erase. I shouldn't erase. I know better. Just as a reminder, work in is always, no matter what, equal to minus integral of P dV over the process. Always, okay? So whenever you see work, you're always doing integral of P dV, which of course has some special simplifications. If the process is isochoric, dV is 0, so it goes away. If it's an isobaric process, P is a constant, so you don't actually have to integrate. You can do minus P delta V. And if the process is isothermal, it's the tough one where P is like nRT over V, and you get that crap with log of V final over V initial. But so there's easy formulas for what this simplifies to in every case. But again, this is always true. Work is always negative integral of P dV. Okay, if you're told the process is adiabatic, that means that Q equals 0 in the first law. So in that case, the first law is just delta E equals W. Okay, so maybe you're asked, or here, I'll sort of write it next to this, delta E thermal equals W then. Maybe you're told, here's an adiabatic process, the temperature changes by this much. How much work was done on the gas? This equation will immediately tell you. If it tells you the delta T, you instantly know what number delta E thermal is, and then you have your answer immediately for what the work was. Or if you're told there's an adiabatic process, okay, that means you're able to use that equation I just wrote. And work of 200 joules is done on the gas. How much does its temperature change by if it tells you the mass? Well, that equation is a one-variable equation now, and you'll be able to finish the problem. Okay, if you have an isothermal process, in that case, the NCV delta T, right, you're always able to use this equation. Sorry for the feedback, by the way. Remember, this is always true. These two things in red, always. And obviously, there's the mass version of that. Okay, if you're told the process is isothermal, delta T is 0. So delta E thermal is equal to 0. In this case, then, if I cross out delta E thermal, I get that Qn is minus work in. So again, in a problem, it would tell you there's an isothermal process, and it gives you the work, how much heat was put in. Immediately, you have the answer. Okay, if you have an isochoric process, that means work is 0, right? Because work is like P dV, but V isn't changing at all. And therefore, in this case, we have delta E thermal equals Qn. So maybe a question says, during an isochoric process, the temperature of an object goes up by this much. So they're telling you delta E. How much heat was put in? Well, you instantly know the answer. It's a one-step problem. Okay. Any questions on this? This is a very, very good problem-solving strategy. Yes? Yes, you will. You're going to do an example on it in a second. Yes? Sorry, say it one more time. I didn't hear. No, his question was, are isobaric and isochoric the same things in here? So no, I didn't write isobaric here. Isochoric means no volume change. So work equals 0 in that case. I should address isobaric processes. That's a good point. For isobaric processes, none of the 3 variables is immediately equal to 0. So that's why I didn't write it here. These 3 cases, it simplifies greatly. For isobaric processes where pressure is held constant, the simplification that happens is that work is equal to minus P delta V. Right? So instead of work just being 0 and being able to cross it out totally, it isn't 0, but it's a lot easier to calculate. You don't have to do any integrals. Sorry, this says P delta V. I wrote it kind of small. Okay, so again, it doesn't tell you work is 0, but hopefully the problem will tell you what P and delta V are, so you'll still know work just as easily. Good question. But again, it isn't one of the Goldilocks 3 there that makes the first law stupid easy. Okay, so those are the 3 common situations, or I guess 4 common situations. Another thing, which I've always called like the emergency ripcord, is if you're in a panic, just check if you can apply the ideal gas law to usually the beginning or the end of the process where you're told 3 of P, V, N, and T, because then you'll instantly know the 4th variable. And at that point, you basically know everything about the gas. You know exactly what pressure it's at, exactly what volume it's at, exactly how much there is, and exactly how hot it is. Once you have that, you have a lot of different avenues of attack on the problem because you know every single variable, you know everything about the gas. Okay, so it's a very good idea if you're stuck, or even if you're just starting a problem and you want additional avenues of attack, just try applying the ideal gas law. Sometimes you're not going to be told 4, and you'll just have to use like Boyle's law, right? PV equals PV final and initial. But if you're told a lot of stuff about the gas, this is a pretty smart strategy. Okay, and for adiabatic compressions, we had this additional tool that was the analog of Boyle's law. It was that P initial, V initial to the gamma equals P final, V final to the gamma. And gamma was a known constant. I forget exactly, it was like 5/3 for monoatomic gases and 7/5 for diatomic. I forget the exact numbers, but it's a known number. So if they tell you what substance, you know it. So in this case, you don't really need to know N and T. Like maybe you only know the initial pressure, initial volume, and final volume. But you should still have 3 out of 4 variables. So this is very useful. And again, there are those alternate forms where you replace P with T and it becomes like V to the gamma minus 1, things like that. And I'm just going to quickly review the example we did last class before we start the next example, because it's not a challenge example, but it's one that it requires an understanding of the subject. So last class we had this example where we had a gas adiabatically expand. And I actually told you a lot of information about the gas. I told you N, T, and pressure immediately. So knowing that I gave you the 3 of the 4 key variables to describe a gas, it might be a good idea to apply the ideal gas law instantly. And sure enough, later in the problem, you end up needing that information. Okay, the first question was about finding the final volume of the gas, which you could do in multiple ways. The immediately obvious way is to use the PV to the gamma equation, because you know every number except 1 in there. Alternatively, you could try and use the ideal gas law, but you'd run into the issue that you don't know the final temperature. So that wouldn't be immediately relevant. So it was just a plug and chug into the PV to the gamma equation. That told you the final volume. Okay, now I ask for the final temperature, and I said that there are 2 ways of doing it. The first way is using, in green at the bottom here, the TV to the gamma equation. Right? It's the analog of PV to the gamma, but it tells you about T and V instead. Or you can use the ideal gas law, since by now, at the end of the process, you know the number of moles, the pressure is halved to 1 atmosphere, and you know the volume. So you know 3 of PV, N, and T. Okay, so as you can see, what I just reviewed, it comes up in pretty good detail in problems. Okay, so I know it was a lengthy review, but I want to have everyone set up for success on this example. If you were confused, raise your hand and have me help you, because A, this appears on the homework, B, it will probably appear on a test, and C, if you feel like you're totally lost, you're probably not. You're probably only like 1 or 2 minutes of explanation off. So flag me down if you run into issues. Okay, so again, this is straight off the homework. I have 2 different samples, and I'm just asking about 2 different processes. They're not like related to each other. In one case, I bring oxygen on an isothermal compression, and then in a second case, I bring it along an adiabatic compression, which is a different kind of compression. Okay. And I tell you the pressure, volume, and number of moles at the end. Okay, the first question is the heat inputted during an adiabatic process, which you shouldn't even need an equation for. Part 2 and Part 3 are where we're going to have to work a little bit, but so stick to your guns. If it asks about heat, you're going to need the first law. If you're asked about initial pressure, final pressure in an adiabatic process, you might need PV to the gamma. Okay? All right, so take a crack at this. Again, I will walk around the room. Please raise your hand if you're confused on this. All right? And by the way, oxygen gas is diatomic, so you'll need to use the appropriate gamma for a diatomic gas. And I'm going to write a formula up here that we had derived a couple classes ago. I called it like a cheaty formula for the work done during an isothermal process. What's the definition of heat inputted during an adiabatic process? What's the definition of adiabatic? Zero heat inputted during an adiabatic process. By definition, that's what adiabatic means. Right, so number 2 is the harder one. Is one of the first things I said during the review. Stuck on number 2, write out the first law. Okay, and I said during isothermal processes, you can just cross out one of the letters. Yes. You can. Does anyone have questions on how I did part 2 of this question? Okay. Questions on part 2? All right, for part 3, you're using this PV to the gamma equation. Right? You can technically get around it using the ideal gas law, but whenever you're told like initial pressure, initial volume, and then either final volume or final pressure, you know every number in this equation but one. So you're going to have to do some algebra on it to get, what am I asking about? PI. But you know every number except for PI, so it's simple algebra. All right, if you plug in numbers in pascals and atmospheres, oops, whoa. Glad to know I didn't mess up the algebra. Yeah. All right, I'm gonna call an end to the example here and take questions. Yes. The pressures? Everything needs to be in pascals always. Otherwise, the multiplications don't always work. You can technically cheat your way around it by leaving some things in atmospheres, but I would just advise always going to Pascal. All right. Questions on how I did this problem. Again, this won't kick your ass on the homework if you don't understand what I'm doing here. Right? Questions on this? One, pretty straight. Yes, you can check it on the homework technically, but when it appears on a test, it's going to double kick your ass. For number one, heat input during adiabatic. Again, by definition of adiabatic, it just means heat input is 0. So 0 without any work. Part two, I see that keyword isothermal process, and I'm asked about heat, which is double telling me from this last slide, it's a good idea, I should write out the first law. And then for an isothermal process, oops, that's supposed to be in green. For an isothermal process, delta E is 0, so the first law gets really easy. The heat in, all I do is find the work in and throw a minus sign in front of it. Okay, so in our problem, to get heat in, all I did was calculate the work, which was this thing in green, which I told you, for an isothermal process, and then put an extra minus sign on the front of it. So I got plus PF VF log of V final over V initial. And if you plug in all those numbers, you get negative 650, which means heat was actually expelled during the process. Now let's check if that makes sense really quickly. You're not always going to be able to do this, but sometimes you can. So I'm taking a gas and squeezing it, but I'm forcing its temperature to stay the same. So basically, as I squeeze it, the gas is trying to heat up, but I'm going to allow it to blow off heat into the surroundings to keep its temperature constant. So it roughly makes sense that I got a negative number. And then for number three, I just use the PV to the gamma equation. If you can't use the ideal gas law and it's an adiabatic process, this is probably going to be the way that you find the final pressure or volume. Again, any questions on how I walked through this? Any questions on how I knew to use a certain equation? All right. So we're going to move on to the Equipartition Theorem, which I sort of already covered the other day. Okay. And the Equipartition Theorem states this. States that the average thermal energy of a molecule, not delta E thermal, this actually tells you the absolute amount of E thermal. It's 1/2 the Boltzmann constant times the temperature in Kelvin. For each degree of freedom, I'm going to call it. So if you have 3 degrees, I'll explain what they mean in a second. For 3 degrees of freedom, it would be 3/2 kT. For 5 degrees of freedom, it would be 5/2 kBT. And again, kB is just a Boltzmann constant. This relates to something I had told you earlier, where capital CV was 1/2 R for each degree of freedom. They're pretty equivalent statements. Okay, but this one actually tells you about the actual amount of thermal energy an atom will have on average at a certain temperature. Okay, this is different than delta E thermal. is NCV delta T. They're related, of course, but okay. So a common case is 3/2 kBT for a monoatomic. I should justify that in a second. And 5/2 kBT for diatomics, for diatomic gases. So E thermal equals these two possibilities, depending on what kind of gas you are. And I'll explain why in terms of degrees of freedom in a second. Okay, if you remember, a degree of freedom is like the number. Oh, yes, question. I don't know off the top of my head. I think it's like 1.38 E minus 23, but don't quote me on that. You can Google it, though, and it's in the equation sheet as well. Good question. All right, so degree of freedom is, roughly speaking, a way that you can move a molecule and have it like physically change. So for a single particle, you can just move it in 3 directions. Strictly speaking, you're talking about there are 3 momentums you're allowed to modify, equivalent to 3 positions. For diatomic molecules, you can translate the center of mass in any of 3 directions, so that's 3. But also, it's like a baton. You can twirl it around this axis or this axis, so that gives you 2 additional possible modes of rotation. Again, it's very, very roughly speaking. There's formal ways to define degrees of freedom, but remembering the numbers in this box is sufficient. But that's where it comes from. Okay, and I'll put this in quotes. Obviously, if you have a bunch of molecules, the total energy is the energy per molecule. I'm going to put this as a subscript or a superscript. This is the thermal energy of one molecule at a certain temperature, and if you have 100,000 molecules, you multiply that by 100,000 to get the total energy of all the molecules. But that's pretty common sense. So obviously, E total equals number of molecules times the E of each molecule. Just important to remember that this is the energy per each individual molecule, not of a whole assembly. It's per each individual molecule. Okay, so I'm going to run through an example that, as every example is, straight off the homework. So I'm told I have 2 moles of oxygen gas sort of spread out in a room, and I tell you it in total has 3,100 joules of thermal energy among all the 2 moles, which is like 12 times 10 to the 23 atoms. Okay, and importantly, remember our formula cares whether the gas we're considering is diatomic or monoatomic. Oxygen gas is naturally diatomic, and I put as a warning on the homework, this corresponding problem uses argon, which is a monoatomic gas. So you have to use 3/2 R instead of 5/2 R in the formula on the homework. Okay, I'll let you guys copy down the question. Okay, so the relation for the energy of each molecule would be, it would be E each equals 5/2 kBT if it were just one molecule. But if I want the total energy, I should multiply this by the actual number of atoms. Okay, so the total energy is related to the temperature like this. Okay, again, I'm using 5/2 because oxygen is diatomic. If it were a monoatomic one, like on the homework, I'd be using 3/2 kT instead. Okay, let's check what variables I have in this equation. Kb is a constant. I'm hunting after T, so I don't have that. I'm told E total, and I'm like sort of told number of molecules. I'm told the number of moles instead. So the number of molecules is the number of moles times Avogadro's number. Okay, so I actually do know n molecules. I wasn't told it directly, but it was easy to find. Okay, so at this point, I know every number in this equation except for T. So I can move stuff around. Okay, I have E equals N, Na, 5/2 kT. By the way, sometimes people will write K instead of Kb. It's still the Boltzmann constant. Again, I know every number in this equation except T. So I can divide, or I can just plug in numbers now and divide over. Okay, this will yield T equals 74.6. Again, that's just from dividing the right-hand side over. Okay, now importantly, this is in Kelvin. Okay, for things like delta T's, we didn't care if we used Kelvin or Celsius because the step sizes were the same. This equation talks about absolute temperature, sort of like how for the ideal gas law you had to use Kelvin because it wasn't delta T, it was T. You need to use absolute temperature, and any result you get out will be in Kelvin. So if I want to convert this to Celsius, I subtract off 273, and I get negative 198.4 Celsius. Questions on my approach to this problem? I might even argue that the formula with the number of molecules in it is more commonly used than the energy of each molecule. And inevitably, when you forget my comments, I will mark this. Use 3/2 on the homework because argon is monoatomic. All good? Yes? Yes, if it's not there, it should be on the formula sheet, but all constants will be given. Again, hypothetically, you should be able to take the test without any note card at all, so I'll give it to you, and if it's not, please let me know. Same goes with, like, if you guys notice that, like, Boltzmann's constant is not on the equation sheet, please tell me. That just means I forgot. Okay, so we're going to do two very quick topics. They're going to be like 5 minutes each, conduction and radiation. The previous stuff on adiabatic compressions is much more important because we're going to use it during engines, which we'll start next class. These are just things I need to talk about briefly. Okay. So heat conduction is, or I guess I should first say, heat conduction and radiation, they talk about rates of heat transfer. Usually we just care about how much total heat is ejected during a process, but these things talk about exactly how fast, how many joules of heat per second are flowing between two objects of different temperatures that touch. Okay, so heat conduction is heat exchange between two objects that touch. I'll call it the heat exchange rate because the equation will be a rate of heat flow. Okay, heat exchange rate between two objects touching. If you put cold concrete and warm air, how fast does heat flow from one to the other? I'm going to sort of modify this definition a bit, but I'm going to do a sketch first. Okay. So technically, it's more about hot object, cold object, and third object in the middle that is actually the vehicle by which the heat gets transferred. For just two boundaries, I don't exactly know how you define that. So I'm going to draw a sketch here. This is going to represent a house. There's going to be a slab of concrete in between, and then the dirt is below. Okay, so we have dirt, house, and then the concrete is in the middle. And the concrete is going to act as a thermal conductor. Okay. And we're going to ask about the heat exchange rate, heat flow rate through the concrete. I think conductor is the right word. Conducting medium might be a better word. Okay, so we're going to ask, if I tell you the temperature of the house and the temperature of the ground, how many joules per second flow between them? Okay, and the equation is that the rate of heat flow, the amount of heat per time, is this constant called K, which is called the thermal conductivity of the material. I'll write that in a second. It's a material constant, so if you use concrete versus brass, it's a different number. Times the cross-sectional area of the concrete, or of the interface with the house with the concrete. I guess I should chop it off right there. Okay, so it'd be the area of like a square slice here, times the temperature difference between the hot object and the cold object, alternatively the two ends of the concrete, divided by the thickness of the concrete. Okay, so we have L is this vertical thickness. A is like, obviously this house is 3D. Okay, so it's the area of the slab. Write it in red. Delta T would be the temperature of the house. Maybe the house is being kept at 20 degrees Celsius and the ground is at 6 degrees Celsius. So delta T is between these 2 points at the end of the concrete. And K is a material constant, which is 0.8 for concrete. And this is in watts per meter Kelvin. Now, I just want to quickly modify my definition slightly. I said it's heat exchange rate between two objects that are touching at a boundary. It's more akin to the heat exchange rate between the upper end of the concrete that's held at a certain temperature, the temperature of the house, and the lower end of the concrete, which is held at the temperature of the ground. So it's more about heat flow through one object, but as you can see, it's also sort of applicable to when two objects touch through a medium. So I'll say between two objects touching or through one object with ends at different temperatures. I had an example for this, but I'm going to skip over it so I can get to radiation quickly. As you can tell, it's probably just going to be a plug and chug most of the time. You're going to be told every number but one in this equation. Okay, and very quickly, we're going to talk about radiation. And it's heat emitted by glowing, by like emitting infrared radiation. So if you just have an object chilling in a room and it's a certain temperature, it gives off heat. You can see it on the infrared camera. Humans you can see very well because we're hot and we give off a lot of radiation, but cold objects not as much. Okay. The equation for the rate of heat emission is that dq dt is sigma subscript SB times A, which is the area of the object, times T to the fourth, which is an extremely unusual thing to see in an equation, something raised to the fourth power. This must be in Kelvin. Sigma SB is called the Stefan-Boltzmann constant. Okay, its value is 5.67 E minus 8. And the units, it definitely wins the competition for the ugliest units I've ever seen. Watts per meter squared Kelvin to the fourth. Okay. Again, any radiation problem is going to be a plug and chug where you're told the area and the temperature and ask what's the rate of heat loss. I have an example. I might start next class with it. All right, I'll see you guys on Friday. Have a good day. Also, office hours today if you need help on adiabatic stuff, and tomorrow.